In this video, we'll dive into the world of conducted emissions, what causes them, how they affect your circuit, and most importantly, proven strategies to mitigate these issues right from the printed circuit board design. Conducted emissions are simply radiated emissions in disguise, and the simple reason for dividing them into conducted and radiated emissions is that it makes testing easier. And the problem with measuring emission below the 30 MHz using the same testing methodology as radiated emissions is that the wavelength of the signal can be in the near field region, leading to results that don't match the reality. And if we measure emissions above the 30 MHz using the same testing methodology as the conducted emission test, we encounter different issues where the cable then can start to resonate at these frequencies, which also yield incorrect results. So the main objective of the conducted emission test is to ensure that the emission levels are under certain thresholds. And this is because if disturbances find a way to escape from the system, they may potentially spread around and then upset also other systems. And one common way for this to occur, if left uncontrolled, is when disturbances are conducted out of the system through the power cords. And what can happen in this scenario is that the conducted disturbance through the power cord, then it might reach the power distribution system. And this is quite important because the structure of the power distribution system is built in a way that resembles a large antenna structure, which can then potentially radiate and upset many other systems that can be susceptible to that. To aggravate the issue, since the power distribution network is built with these longer cables, this gives also the possibility for large wavelength to find a radiative structure and then potentially radiate. And this is why the regulatory bodies like the FCC and the CISPR impose limits on these emissions so that we can create an environment with fewer emission pollutants where the system then can instead work in harmony with each other. In the same way, we also want to prevent not only that our system has limited emission levels, but also that its susceptibility or immunity to these emissions is controlled, and then providing a robustness for our system. One of the most common ways susceptibility or immunity issues arise is through the disturbances reaching our system, such as when lightning strikes on the power transmission line, which is providing power to the installation. Some of the disturbances may also cause the loss of power for long periods or short outages. And in the former case, the system are not expected to maintain operation. However, in the latter case, for example, when the circuit breaker is attempting to reestablish the power, then the product is expected to maintain normal operation without the loss of the data or its function. So in order to test the system and to verify that the level of emission is within a certain safe range, the regulatory agencies such as we mentioned, the FCC and the CISPR, have established the limits with which the system must comply. And a typical range of the frequency to which the system are tested against the conducted emission test is from the 150 kHz to 30 MHz. However, this limit may vary depending on the specific standard that the system has to comply with. So it's not always the same. And within this range of frequencies, the FCC and the CISPR have also specific requirements to be met for different ranges of frequencies. Conducted emissions are also classified into different categories based on the frequency range and the standards they comply with. And the most common classes for conducted emissions are Class A and Class B. The Class A typically applies to industrial environments where there are fewer restrictions on emissions, and devices in this class have emission limits set at a higher level compared to the Class B. In the Class B, devices in this class instead need to meet the stricter emission limits, and this is important for devices using residential or commercial settings, where there is a need to minimize interferences as much as possible. And these classes basically help ensure that electronics devices meet the specific standards depending on their intended use and also on the environment in which they will be operating. Let's now look at the values of the limits for Class A and Class B for conducted emissions. So for Class A digital devices, the quasi-peak limit is of 79 dB microvolt from 150 kHz to 500 kHz. And then from 500 kHz to 30 MHz, the quasi-peak limit is of 73 dB microvolts. For the average limit, which is the light line, the limits are set to 66 decibel microvolts and is from 150 kHz to 500 kHz. And then from 500 kHz to 30 MHz, the average peak limit is of 60 dB microvolts. The Class B digital devices, the quasi-peak limit from 66 decibel microvolt to 56, and it from 150 kHz to 500 kHz, and then from 500 kHz to 5 MHz, the quasi-peak limit is of 56 dB microvolt, to then again increase to 60 dB microvolt from 5 MHz to 30 MHz. For the average limit, which is the light line, the limit goes from 56 decibel microvolt to 46, and this is from 150 kHz to 500 kHz. And then from 500 kHz to 5 MHz, the quasi-peak limit is of 46 dB microvolt, to then again increase to 50 dB microvolt from 5 MHz to 30 MHz. One of the common approaches when doing pre-compliance testing before going to certifying at the EMC lab is to keep the system emissions at least 6 dB below the required limits. And this will help to account for the differences between different laboratories and instruments, also due to the measurement uncertainties. I personally recommend staying even below the 10 dB margin, if possible even below the 15 dB margin. However, I know that this is sometimes very difficult to attain, so 6 dB is a common practice. So in order to conduct a test for conducted emissions, the line impedance stabilization network, which is also called a LISN, should be used. And the LISN is sometimes also called artificial main network or AMN. So the LISN is used to make the measurement comparable between the labs and measurement, and thereby stabilizing the impedance seen by the product outlet into the power distribution network. So the LISN has basically three important functions when conducting the measurement. The first function is to provide a constant impedance to the power outlet, and it has to maintain it also over the frequency range of the conducted emission test. The second function is to filter out the noise that is not part of the noise generated by the product, allowing only the conducted emission of the product to be measured. And additionally, the LISN should be able to transfer the required power at 50 or 60 Hz, depending on the market, so that the product can operate. As we can see in this slide, we can see that the LISN is connected between the power distribution network and the device under test, which is also called the DUT. And the job of the spectrum analyzer connected to the LISN is to measure and report the level of the conducted emissions. To further explain the testing setup and also to understand what we are truly measuring during the conducted emission test, we need to take a closer look inside the LISN circuit. The value of these components will vary depending on the type of the test that we are performing and ensuring that the 50 ohm characteristic impedance is matched throughout the entire frequency range of the test. So let's explain the role of each component in these slides. So we have the 50 microhenry inductor, which is used to block the external noise from the power distribution system. Then we have the 1 microfarad capacitor divert the external noise from the commercial power side of the LISN, preventing this contamination of the measurement signal. Then we have the 0.1 microfarad capacitor, which prevented the DC overload at the input of the spectrum analyzer. We also have the 1 kilo ohm resistor, which serves as a static charge path to discharge the 0.1 microfarad capacitor if the 50 ohm resistors are then removed. And then one of these 50 ohm resistors is for the input impedance of the spectrum analyzer, while the other 50 ohm resistor serves as a dummy load, ensuring in fact that the impedance between the phase and the safety wire and between the neutral and the safety wire remains at 50 ohm all the times. Then the green color arrows that you see are the currents IP, which is going from the DUT to the phase wire, and then the current IN, which is going from the DUT through the neutral wire. So one important thing is that for the range of frequencies of the test, the LISN circuit will result in the simplified circuit that you see in the slide here, where the inductor becomes an open circuit at the frequencies of the test, while the capacitor here becomes a short circuit over the frequency range of the measurement. The voltages measured during the test are these VP dash and VN dash, and they're measured between the phase wire and the safety wire and between the neutral wire and the safety wire. So these two voltages are measured throughout the entire frequency range of the test, and they must always remain below the specified limit set by the test. And this also explains why conducted emissions are specified in terms of voltages, even though what we're actually measuring is the conducted emission current. So by using this Listen circuit, we can measure the noise current, which is related to the product through both the phase and also the neutral. So really the PCB design task in this case is to design the electronic product so that no current flows through the 50 ohm resistors of the Listen. And this also implies that if there is a current flowing through the 50 ohm resistors of the Listen, and if the current in the frequency range of the measurements exceed the specified limits of the test, this would result in a failure of the conducted emission test. This, in fact, further emphasizes the importance of carefully designing the PCB layout and the overall system to avoid any signal coupling to the power cores and then being detected as a current flowing through the Listen resistor. Now we will separate the IP and IN currents into the differential mode and mode components, and this will be important in understanding the influence of each of the modes. So we can define the current IP as the sum of the common mode current component IC and the differential mode current component IT. And the same we can do for the current IN, and define it actually as the subtraction of the differential mode current components from the common mode current components. And then if we play around with the substitutions and we solve for IC and ID, we can find how the common mode currents and the differential mode currents are influenced by the phase current, which is the IP, and the neutral current IN. So now we can rewrite the voltages of VP dash and VN dash in terms of the phase and the neutral current, remembering also the relationship they have with the differential and common mode currents. And this means that by measuring the voltages across these 50 ohm resistors with the spectrum analyzer, we can find the differential and the common mode currents. One important aspect here is that the differential mode currents we observe are not functional 50 or 60 Hz power line currents required for the normal operation of the device. And also the common mode currents returning through the green wires are unwanted and are not typically intended as a part of the design. And this is crucial because the green safety wire is intended as a safety measure when a fault occurs. So this is not meant to carry currents during normal operation. And therefore, when the green wire carries current, as in this case with high frequencies, which is carrying common mode currents, it can result in the failure of the regulatory standards. Okay, now that we have seen how the test is conducted and what we're measuring, we can further investigate the problem itself. And since we are discussing the conducted emission into the power cores, we need to look into the block or circuit which is connected to the power cord, and in this case is the power supply. So the power supplies that you are going to examine are the switching mode power supply, which are also called SMPS. Today, power supplies have reached very efficiency levels above the 85%, and they're also widely used in our electronic products. However, the high efficiency of the power supplies unfortunately comes at a high cost in terms of electromagnetic compatibility. And the reason behind this is that for these power supplies to be so efficient, the switching transition time has to be as fast as possible. And this means that a large amount of energy has to be condensed and transformed in a very short amount of time. And for us as designers, this translates into a very sharp transition in times, which is, thanks to the Fourier transform, we know they contain a high energy harmonic content. In fact, the sharper the signal, the more high energy harmonic content there is, and the more high energy harmonic content, the more energy there is. And the problem with this high energy harmonic content is that the energy contained in these harmonics needs to be contained and then controlled in order to avoid emissions and to channel the energy where it actually needs to go. And after all, what we're measuring with the EMC test is exactly how this energy moves and how high or above the imposed limits this energy is. And to better understand what happens during the conversion of the energy and also to understand the difficulties related to this process, we're going to analyze a general flyback converter. So the circuit here is simplified so that we can visualize only the elements that are more important to us. And at the first stage of the converter, we have the full bridge rectifier, whose job is in fact to rectify or, let's say, straighten the AC voltage at its input. And the rectifier then feeds the converter waveform to a filtering capacitor, whose job is to further filter these rectified waveforms and to stabilize them at a voltage close to the peak voltage of the waveform. At this point, in here we have also a PWM controller, whose job is to monitor the output of the input capacitor and then to feed the PWM signal to the main switching transistor. Then the transistor job is to basically chunk the energy into square waves that are fed to this transformer. And then the transformer job is to isolate the primary side of the converter from the high voltage, but also to further step down its voltage to its desired output in the secondary side of the transformer. Then in the secondary side of the transformer, this voltage is further rectified and filtered with a LC filter, which is producing this DC output. And as mentioned before, the switching transistor, in order to optimize the power efficiency and to reduce the losses, will try to spend as little time as possible in the linear region, and it will produce a trapezoidal wave output. And in order to produce this trapezoidal wave output, its transition time has to be as short as possible, so that its rise and fall time is usually in the order of the nanoseconds. And as I briefly mentioned before, we know from the Fourier transform that in order to generate the square wave signal, we need to have an unlimited series of harmonic sinusoidal signals whose frequencies are multiples of the main switching frequency. And this is where the high energy harmonic content actually is. So the SMPS will then have multiple sources of noise, which are also categorized as normal operation noise, which comes from the differential mode noise, and the common mode noise, which comes from the parasitics within the circuits. So let's see what the major contributors of common mode noise sources are in this SMPS power supply. So the first is the transistor to heat sink capacitance, where the heat sink is usually connected to the safety green wire. Then the second is the interwinding transformer capacitance between the primary and the secondary side of the transformer. And the third is the straight capacitance to the earth ground from the wiring and from the PCB traces to the earth ground. And these 3 points, since are the sources of common mode currents, will present the challenging EMI issues. And the question for us designers is, how can we fix these issues at the design stage? As discussed in other lessons and also in some other of my articles, there are 3 possibilities to solve EMC issues, and these possibilities are related to either the source, the path, and or the victim of EMI. So we can reduce the source of emissions, for example, taking action on the switching transistor and either changes the switching frequency or slowing its switching times. And unfortunately, this can result in lower performance and also increase the losses, as we directly impacted the switching wave. And by changing the frequency, it will only shift the level of emission to other frequency ranges, which may not really solve the issue. The other option that we have is to disrupt the path where the emissions propagate. And this will mean finding a way to interrupt the common mode current loop and eliminate the parasitic capacitance. And the third option, which is the final option, is to increase the immunity of other devices to the emissions created by our device, which is not really an option because we cannot obviously control all other devices that are going to be around the power supply. So let's see what are the different possibilities to fix the issues mentioned here by using these methods. So to solve the first issue, all the straight capacitance between the heatsink and the transistors, we have a few options. And one is adding a Faraday shield between the transistor and the heatsink. And to do that, we will have to use special thermal pads that integrates the shield and then connect them to the transistors. And we have already several vendors that offer this solution. As a second possibility, we can increase the thickness of the washer and use a thicker washer, which will then reduce the capacitance. And the third option is to leave the heatsink floating. But in this case, we have to ensure that the user has no access to the heatsink and cannot touch it. Otherwise, this can create a shock hazard situation for the user. For the second issue, can be fixed by either increasing the distance between the 2 coils of the transformer or by using one with a Faraday cage. However, this may result in increase the size of the transformer and sometimes also the cost. And the third issue can be resolved by proper layout of the PCB board and with proper system wiring, so that the straight capacitance of the printed circuit board to the earth to ground is reduced. The proper PCB layout techniques are also covered in many of my other lessons and courses if you want to take a look at it. The main takeaway though here is we have to think in terms of parasitic paths that emerge from the system design and connection, and especially thinking in terms of how these parasitic paths will influence the test at the specified frequency range of the test, and also can result in effective current loops for the common mode currents. Now, let's address how to solve the issues related to the differential mode currents. The primary source of the problem when dealing with differential mode currents is usually attributed to the non-ideal characteristic of the input capacitors, which is meant to filter the output of the rectifier. And ideally, the capacitor at a higher frequency acts as a short circuit. But unfortunately, this is only true for the ideal components. And the issues with real components, such as the capacitor, is that in the real-world application, it will only exhibit the capacitance behavior we desire, but also we have an equivalent series inductance, which is called the ESL, and an equivalent series resistance, which is called the ESR. And the problem with having these two parasitic impedances is that they will create all the preferred paths for certain harmonic frequencies contained in the switching currents. And this means that the currents will not flow through the capacitor, thus generating these additional differential mode current loops. And the larger the value of the capacitors, the larger these parasitics usually become. And unfortunately, we don't have many other ways to tackle these issues than to reduce the parasitic effects of the capacitor. And in particular, we want to be careful in selecting a capacitor with small ESL and ESR so that the differential mode current is as small as possible. And we want to provide the switching current in the path of least impedance through the capacitor and throughout the whole frequency span of the test. And this means that the key to reducing differential mode currents and hence passing the conducted emission test is to really focus on the impedance of the capacitor, taking into account also the parasitic effects. The next issue we need to cover is related to the source of noise, which is caused by the rectifier used during the rectification process, and different types of diodes can be used for the rectification process. However, the one subject to more EMI issues are the fast recovery diodes. And fast recovery diodes are preferred by the designer as they improve the efficiency of the power supply, but typically these choices results in more issues in the EMI realm. And as usual, this will impose the trade-offs between the power losses and the EMI performance. So where is the problem with this rectifier diode? So the problem is caused during the reverse recovery time of the diode when the charge is accumulated in the diode junction during the forward bias of the diode, hence during the conduction, and when it's suddenly removed, produces this sharp negative spike of current. And the steeper the spike, like we said, the more energy need to be moved fast, and the more high energy harmonic content is present in the signal, generating these types of pulses. And typically the issue is more common on the secondary side of the SMPS because this part of the supply usually deals with the higher currents than the primary side, where the voltage is usually higher than the current. But this does not mean that the rectifier in the primary side of the power supply should be left without consideration and should be taken also for granted, because of course we will have to take them into account as well. So these differential currents produced during this reverse transition time can then find the ways to couple back to the primary side of the transformer and ultimately to the power distribution network. And it's important to know that this effect is also common in switching transistors, and in particular for us, these effects need to be taken into consideration for switching transistors of the power supply. And one of the possible and actually very effective solution for this fast switching differential mode currents is to implement a RC filter across the rectifier. And this allows filtering out the noise of the differential mode currents. Unfortunately, the side effect of these techniques are that the energy will now be dissipated through the RC filter, which also increases the power losses. And then the voltages and current across the used device can also increase. And one thing worth mentioning here is that the principle that we have just discussed so far can also be applied to the DC to DC converter. Finally, let's see how to apply the filters for both the common mode and the differential mode in SMPS. And the filter we see in here is a typical EMI filter and is used to suppress both the common mode currents and the differential mode currents. And the Y capacitor, together with the common mode choke, form the common mode suppression section, while the X capacitor is used to suppress the differential mode side. The values and the characteristics of this capacitor used in the filters are regulated by the safety agencies. And for example, for line-to-earth connection, a special capacitor, which is called the Y capacitor, is used, which is listed and also approved by the safety agencies, such as the underwriting laboratories or UL, and its value is also limited to limit the leakage current, since the leakage current are considered as a shock hazard and are also regulated. This Y capacitor is also special because in the case of failure, it does not create a short circuit, but it will fail open. And this is important because in this way, the phase, which is connected to one side of the capacitor, is not going to be connected to the earth system, which is typically also connected to the chassis and therefore can put the user in an hazardous situation. And similar safety regulation requirements also apply to the X capacitors, which are intended for the line-to-line operation. So for building these filters, the first thing that needs to be chosen is the common mode capacitance, and this is selected as the sum of the two capacitors, which are then placed parallel from the common mode current point of view. And the total capacitance is derived from the safety current leakage requirements of the safety agency. And once the current leakage is determined, then the total capacitance is also determined, which is based on this limitation, and is typically also divided in two between the two capacitors. Now, regarding the placement of the components, the filter needs to have the X capacitor side facing the high impedance connection with the lesion, while the two common mode capacitors should face the power supply side, as is presented in here. And the two Y capacitors need to be connected to the metallic filter enclosure to optimize their effectiveness and also to reduce the stray inductance of the connection. Also, for the filter to be effective, it should be placed as close as possible to the enclosure where the power cord enters as an input. And this is essential because if the noise coupled into the circuit after the filter stage, then the filter becomes ineffective in suppressing or reducing that noise. And filters are designed to block or attenuate unwanted frequencies up to the point where they are placed in the signal path. So any noise that enters the system beyond the filter will bypass its intended function.